Hey everybody, it's Brandon from STEM Tutor Club. Today's going to be a quick one. I just wanted to go over a good way that I found to think about how to convert between radians and degrees. So just looking at the unit circle here, you can see that pi over 6 would correspond to 30 degrees, pi over 4 to 45, and then so on and so forth, pi over 2 to 90. Um, it's not really feasible to remember all of these, but luckily there is a formula to convert between them. But that formula can be a little bit unintuitive, so that's why I thought I'd explain the way that I think about this. First, let me explain the way it's normally taught in class. So this is the way that it's normally taught is that when you want to convert between degrees and radians, you just multiply by pi divided by 180. So for example, if we had 30 degrees and we wanted to convert that into radians, then we would multiply by pi divided by 180. 30 divided by 180 can be simplified to just pi over 6. So 30 degrees would equal pi over 6 radians. So you can see that it's correct, but I think there's a different way or a better way. And just to show this example, when we're going from radians to degrees. So for example, if we started at let's say pi over 4 degree or pi over 4 radians, and then we wanted to convert that into degrees, how would we do that? 180 divided by pi, and then you can see that the pi's cancel out, and then 180 divided by 4, what would that equal? Well, 180 divided by 2 would be 90, and then dividing by that by 2 would equal 45. So these formulas are correct, but it can be hard to remember pi over 180 or 180 over pi, and it can be confusing. So there are two things that I think, or two different ways that I think about this. The first way is that instead of using pi and 180, I like to use 2 pi and 360. Now you get the same thing, like algebraically they simplify to the same thing, but I think it makes a lot more sense to think in terms of 2 pi and 360 degrees rather than by pi radians and 180 degrees. This really only represents a semicircle, whereas to me it makes more sense to represent the entire circle. And just explaining what I mean by that, if you focus on the 2 pi radians or 360 degrees, then it's pretty straightforward. It's just an entire revolution around the circle. You don't, whereas the other formula makes it seem like you're only going halfway around the circle. Now, obviously, there's 360 degrees in a circle, so that there should be no surprise there. But why would there be 2 pi radians going around a circle? Well, the reason for that is that it really comes from the formula for circumference. So the circumference, as you know, equals d pi, and diameter is really time or is really 2 times r. So this entire formula can be thought of as 2 pi times r. And this is just the normal formula for the circumference that you're used to. And this actually is where the idea of radians come from. The radian comes from an angle measure that when multiplied by the radius gives you the circumference, or at least the partial circumference for that arc. So in my mind, it's a lot easier to work with 2 pi than pi. That's more natural because that's a full revolution. So that's one thing, but even if you remember that, you can still get confused about having 2 pi in the numerator and 360 in the denominator, or vice versa. So, like, in other words, you might confuse the formula for going from degrees to radians with the one from going from radians to degrees. So, how do you keep that in track, or how do you keep track of that? The best way that I've found to think about that is to treat each unit, so degrees and radians, like normal variables in algebra, and basically apply whichever one that you need in order to get the right units at the end. So to explain what I mean, let me explain the wrong way to do this. So if we start off at 30 degrees and we want to convert to radians, you might think if you're having trouble remembering which one's which, you might think that 360 goes in the numerator. So we'll get 360 and then divided by pi. And if we calculate that, we would clearly go from so 3 times 360, that'll equal obviously a huge number, and then we'll have pi in the denominator. That in and of itself is sort of a clue that it's not right, because pi should always be in the numerator when you're converting to radians. But if you just look at the dimensions, or just look at the units, so degrees, radians, you'll get basically degrees squared in the numerator. You have degrees times degrees divided by radians, which is not what you want. Remember, the final answer that we wanted was just radians. So the final answer that we wanted was just radians. We get this kind of weird, ugly formula. However, if you try the, oh, and this, sorry about that, that should have been 2 pi, by the way. However, if you try this other option, so 2 pi radians over 360 degrees, so basically just swap them. Assuming you remember 360 and 2 pi, now we're just swapping them for the order. Well, now what happens? So now, first off, we get pi in the numerator, which gives us more confidence, but just purely looking at the units, we get degrees times radians divided by degrees. And then the degrees in the numerator and the denominator cancel, and then we're just left finally with radians, which is what we want. Now that is a little bit unusual. You might not have basically done algebra with units, but you actually can do that. It turns out that it actually works still, and that's an entire topic called dimensional analysis that you might come across in class. So anyway, that's all I wanted to talk about today. I hope you at least learned a nice trick to remember this conversion formula more easily. So hopefully you don't get stuck on radians and degrees in the future. See you next time.